Amid the vast stillness of the cosmos, there lies a boundary so small that human thought grows quiet. The Planck Length, a place where space loses its shape, and time becomes no more than a fragile breath. Tonight, we drift toward that frontier, where science softens like the last glow of a candle, and every law carries the weight of an unnamed mystery. If this stirs a touch of wonder in you, a gentle curiosity, leave a comment as a sign that another mind is awake beneath this same quiet sky. And now, what waits for us beyond this delicate veil? The limits of the cosmic microscope. When we try to look deeper into matter, to see what lies beneath the familiar layers of atoms and particles, we are really asking the universe a question as old as thought itself. What lies at the bottom of everything, and can we ever truly reach it? Physicists have spent a century peeling back these layers, exchanging gentle light for high-energy probes, trading the softness of waves for the sharpness of electrons, and finally for beams accelerated almost to the speed of light. Each step forward reveals a new truth, but also a new silence. Light, for all its grace, carries a limitation woven into its nature. Its waves are simply too large to reveal the tiny patterns carved into the heart of matter. The atom is far smaller than a wavelength of visible light. So when light touches it, the details dissolve. Richard Feynman once said, "Nature isn't classical. Damn it. And if you want to understand nature, you must make it quantum." That truth becomes painfully clear at these small scales, where classical tools lose their reach. To go further, scientists turn to electrons, their wavelengths shrinking naturally as their energy rises. Suddenly, atoms became visible, then nuclei, then the quarks dancing at the center of protons. It felt, for a brief moment, as if zooming was infinite, that the universe would keep unfolding like a lotus blooming into the dark. But the deeper we look, the more the universe pushes back. Energy, when focused into a tiny region, becomes more than a tool of vision. It becomes a weight upon space-time itself. Einstein reminded us that mass and energy are one, two faces of a single coin. So when we pour immense energy into a microscopic point, space-time begins to bend. At higher energies still, it curves violently. And if we press too far, the region collapses, forming a tiny black hole where our observation should have been. Stephen Hawking once remarked, "The closer you get to a black hole, the more time seems to stop." At the smallest scales, time and space themselves tremble under the strain of our curiosity. This is where the idea of the Planck length emerges. About 1.6 times 10 negative 35 meters. Smaller than imagination. Smaller than metaphor. If a proton were the size of the Earth, the Planck length would be smaller than a single atom on that Earth. At this threshold, space is no longer smooth, no longer a stage, but a flickering foam of uncertainty. John Wheeler called it quantum foam, a restless sea where geometry rises and collapses like breath. This limit is not imposed by technology, but by nature. Increasing energy to see smaller regions only invites gravity to close the window, until it seals completely at the Planck scale. It is as if the universe whispers, gently but firmly, no further. And yet this boundary tells us something profound. We may not be able to zoom forever, but we can understand why. The Planck length is not just a number, but a reminder that our concepts of distance and time are approximations, useful at human scales, but fragile at the edges of reality. Some theorists believe that below this limit, spacetime might be quantized, built from tiny loops of geometry. Carlo Rovelli wrote, "Space is not what it seems. It is a network of quanta." Others imagine vibrating strings, their lengths setting the minimum scale like notes that cannot be shortened. Brian Greene described the universe as a symphony of vibrating strings. Both perspectives, though different, hint that sharpness is an illusion. Nature softens before it breaks, blurs before it shatters. What moves me most, as both a scientist and a storyteller, is how the universe protects its own foundation. We often think of knowledge as a ladder that stretches endlessly upward and downward. But the Planck scale teaches humility, reminding us that even the act of looking has limits. And from this, a personal lesson emerges. Not everything must be seen to be understood. Not every mystery must be cut open to reveal truth. Some truths are felt through symmetry, through pattern, through the gentle resistance of nature's own boundaries. When we reach the edge of the visible, what we find is not darkness, but a soft invitation to imagine. Beyond the Planck length, the universe doesn't end. Only our tools do. And perhaps that is where wonder begins. In the quiet drift of thought, as you listen to this in the calm of night, remember that the smallest scale of reality is not a wall, but a whisper. A reminder that beneath all form, all matter, all structure, lies a mystery spacious enough for both science and dreaming. And somewhere in that silence, the universe waits, patient and shimmering, for the next question we dare to ask. In the quiet spaces between atoms, in the calm breath of the universe where matter begins to lose its familiar shape, there exists a simple truth that reshapes the way we see the world. We cannot look at an atom with light, not because the atom hides from us, but because the light itself is too large, too gentle, too wide in its ripples to reveal such delicate architecture. A wave can only uncover what is bigger than its own crest, and visible light with its long, sweeping wavelength washes over the atom like tides over a grain of sand. Richard Feynman once said, "Nature isn't classical, damn it." And at the atomic scale we finally understand what he meant. Light that paints galaxies and warms the mornings of Earth simply cannot fit into the tight embrace of quantum space. It is a humbling realization, one that tells us even our most trusted senses have boundaries written into the fabric of reality. When we shine light onto an atom, the wave is too broad to resolve the delicate core. The electrons, the proton, the very contours of its quantum identity. It is like trying to read a whisper with the crashing sound of the ocean. Yet the universe always offers another path for those willing to listen. And that path arrives not through light, but through matter itself. Electrons, when guided and accelerated, shrink their wavelength to astonishing smallness. A moving electron becomes a wave, a living crest of probability. And by tuning its energy, we tune its reach. Louis de Broglie captured this miracle in a single idea: that every particle has a wavelength, and every motion becomes a rhythm. It was a revelation that turned matter into music, and physics into a dance of frequencies. Because of this, electrons can reveal what light cannot. They slip between the hidden folds of atoms, their short wavelengths embracing the smallest structures without drowning them in destructive energy. Light must strike hard to become small, and in doing so, it destroys what it tries to see. X-rays, though powerful, carry energies so fierce they tear electrons from their orbit, unravel crystals, and scorch the delicate fingerprints of matter. What they reveal, they also break. Electrons do not. They whisper instead of shout, glide instead of strike, and their gentleness gives birth to the electron microscope. Ernst Rusker dared to imagine what no one had seen, and in 1931, he built the first machine that allowed humanity to peer into the unseen geometry of life. For the first time, the boundaries of perception expanded inward, revealing cells, molecules, even the ghost-like silhouettes of atoms as shadows trembling in the void. This shift from light to electrons marks more than a technological leap. It marks a spiritual one. It reminds us that the universe does not reveal itself through force, but through resonance. We look deeper by matching the rhythms of matter with tools that share the same song. Still, as we shrink our vision and drift toward the heart of the atom, another truth gently rises below us. The more we try to see, the more energy we must gather, and the more our observation begins to disturb the quiet balance of quantum nature. It is a reminder that knowledge is never free, that the act of seeing shapes what is seen. I often think of something Einstein said: "The more I learn, the more I realize how much I don't know." At the atomic scale, this becomes literal truth, because every increase in energy sharpens one line while blurring another. We trade clarity for disruption, insight for disturbance, sight for consequence. And so electrons become not just tools, but teachers. They show us that the universe is not meant to be conquered by intensity, but understood through harmony. Their gentle waves remind us that subtlety is often stronger than force, that patience uncovers truths violence can never touch. This is a lesson I carry deeply, and one I believe echoes far beyond science. We learn more from listening than shouting, from quiet curiosity rather than harsh certainty. When I watch an electron microscope reveal a lattice of atoms, shimmering like constellations in miniature, I feel the same awe I feel when gazing at the night sky. It is the same story, the same architecture, the same ancient pattern repeating from the smallest scale to the largest. As above, so below, and as within, so without. Even today, as theories of quantum gravity attempt to unify spacetime with the dance of subatomic waves. The lesson remains. Light is the language of the cosmos, but matter is the language of the atom. We need both to understand the whole. Carlo Rovelli once said, "The world is not made of things. It is made of events." And in the quiet glow of an electron image, I finally understand him. Atoms are not objects, but happenings, vibrations, patterns in an ocean of possibility. Perhaps that is the lesson hidden beneath all of this, that the universe is not revealed by force, but by tuning ourselves to its frequency. When we stop demanding answers and begin listening to the song beneath the noise, clarity arrives. If these reflections stir something in you, if the beauty of the very small opens a quiet space in your mind, I would be grateful for a gentle like or a soft tap on subscribe. Not as a transaction, but as a way of keeping this calm corner of the universe glowing a little longer. And if you feel called to share what this journey reminds you of, your comment may become a small light for another traveler wandering through the silence. In the end, the question of why light cannot see atoms, and why electrons can, is not just physics. It is philosophy. It is a reminder that every tool has a domain, and every truth a proper scale. The universe invites us not to push harder, but to choose the right perspective, the right wavelength, the right rhythm. And when we match that rhythm, even the smallest things unfold like stars blooming in the dark. Amid the quiet breath of the universe, there is a question that seems almost innocent at first. Are protons and neutrons truly solid spheres, tiny marbles at the heart of every atom? Or is something deeper, something more fluid and mysterious, moving within them? This question has followed physics for more than a century, and in its pursuit, we have slowly uncovered a world that refuses to sit still. A world where matter is not hard, not fixed, but dancing. The first whisper of this truth came more than 100 years ago with Rutherford's gold foil experiment, a simple setup, a beam of alpha particles, and a thin sheet of gold. Rutherford expected them to pass straight through, as if through a soft mist. But some bounced back. Not many, but enough to tell a story that shook the foundations of science. It was almost as incredible, he later said, as if you had fired a 15-inch shell at tissue paper and it came back to hit you. That single observation revealed that the atom was mostly empty space, its mass condensed into a tiny nucleus, unimaginably dense, defying every expectation of the time. But even then, the nucleus itself remained a shadowy place. Scientists knew it contained protons and neutrons, yet they did not know whether those particles were the end of the story or merely another doorway. And as technology grew more powerful, curiosity pressed us to look deeper. By the 1960 seconds, the quest for the nucleus's internal structure reached a turning point at the Stanford Linear Accelerator Center, a 2-mile-long tunnel, guiding electrons to nearly the speed of light. When these electrons slammed into protons, they scattered in patterns unlike anything expected from a solid object. Instead of bouncing in a smooth, uniform way, They ricocheted at sharp angles, as if hitting small, concentrated regions of charge hidden inside the proton. It was the moment humanity realized that protons were not indivisible, that they held secrets within them. Those secrets were named quarks, a term borrowed by Murray Gell-Mann from James Joyce's playful phrase, 3 quarks for Muster Mark. But the quark was not just a whimsical idea. It was a revelation that matter itself had layers, that beneath every particle we thought was fundamental lay smaller building blocks. The discoveries at SLAC did not merely refine physics, they rewrote it. And yet, even quarks were not the full story. The deeper physicists looked, the more they realized the proton was not a simple container of 3 quarks, but something more like a storm, a restless sea of quark pairs appearing and disappearing, driven by gluons, the carriers of the strong force. If you could shrink yourself to that scale, if you could float within that subatomic ocean, you would not find solid walls or smooth surfaces. You would see motion, flicker, vibration, energy dancing with energy. As Richard Feynman once said, the world is much more interesting than any one person ever expected. What binds this swirling chaos together is the strange nature of the strong force. Unlike gravity or electromagnetism, it does not weaken with distance. Instead, it grows stronger as you try to pull quarks apart. Like stretching a cosmic rubber band, the tension increases, and if you pull too far, the energy becomes so intense that it creates new quarks instead of letting the originals escape. This is why quarks are forever confined, never found alone. The universe keeps them wrapped in their tiny storms, hidden behind a veil of gluon energy. In this place, what we call a particle is not a solid bead but a pattern in a field, a ripple, a resonance. And when you step back from that idea, when you contemplate it in the quiet of a late night, it becomes strangely beautiful. Matter is not a thing, but a song. Some physicists describe the interior of a proton as a quark-gluon plasma in miniature, a kind of echo of the early universe. Others speak of it as a wave packet, a probability cloud, a shimmering geometry constantly forming and dissolving. What strikes me most is how this image challenges our intuition. For centuries, we imagined the world as built from tiny, solid objects. Yet, when we finally learned to look closely, the solidity vanished. This is where the story begins to touch what happens at the Planck scale, the realm where even quarks and gluons lose their familiar identities, where spacetime itself trembles with uncertainty. Stephen Hawking once wrote, "At the smallest scales, the fabric of the universe is not smooth but foamy." And when I think about the proton, with its restless swarm of quarks, its ceaseless exchange of gluons, I feel as though we are already glimpsing that foam. The deeper we zoom, the more the boundary between matter and spacetime begins to blur. A quark is no longer a tiny hard particle, it is a vibration in a quantum field. A gluon is not a thread tying quarks together, it is a pulse of the strong force emerging from the geometry of the field itself. And the proton, far from being solid, becomes a tiny world of turbulence, held together by rules that defy classical thought. When I reflect on the SLAC experiments, on the images reconstructed from the scattering data, on the mathematical models that followed, I hear the quiet echo of a lesson that repeats itself throughout physics. The universe is not made of things, it is made of relationships. Quarks exist only in relation to the gluons that bind them, and the gluons exist only in relation to the quarks they influence. Matter is a tapestry of interactions, and we are its temporary observers. The idea of confinement, the impossibility of isolating a single quark, carries a deeper philosophical resonance for me. It reminds me that nothing exists in complete independence. Everything is tied to something else. Even the tiniest components of matter are locked in communion, bound by forces that shape and define them. And perhaps that is the quiet lesson hidden inside the proton, beneath its storm of quarks and gluons, beneath the seething energy of the strong force. At the smallest scales, nature does not isolate. It unites. It tells us that solidity is an illusion, that certainty is temporary, and that everything we touch is part of a deeper, shared vibration. In the end, when we peer into the proton, we are not just studying matter. We are touching the echo of the early universe, the remnants of the cosmic furnace where everything began. We are watching the choreography that shaped every star, every planet, every human heart. And when the mind grows quiet enough, when we let the science soften into something almost like poetry, we can hear that choreography whisper, "You are made of this dance too." So the next time you imagine a proton, do not picture a tiny solid sphere. Picture a storm, a song, a vibration held together by the most powerful force nature has ever woven. And remember, as physicist Brian Greene once said, at its most fundamental level, the universe is music. If there is a lesson in this gentle chaos, it is that true understanding does not come from imagining matter as rigid. It comes from accepting its fluidity, its motion, its shimmering uncertainty, and from seeing, in the trembling heart of a proton, a reflection of our own ever-changing place in the vast, breathing universe. Amid the quiet hum of the universe, there rises a question that feels both scientific and spiritual. A question that glows at the edges of human curiosity. Can the Large Hadron Collider truly see through the Higgs veil? Or does it merely brush its surface like fingertips on frosted glass? The thought alone carries a kind of stillness, because the Higgs field is not just another idea in physics. It is the silent ocean through which every particle in existence must pass. Peter Higgs once whispered that the field is like a kind of universal molasses, slowing particles down and lending them the weight that makes stars possible. And so when we ask whether the LHC can see through that field, we are really asking whether human instruments can peer into the breath of creation itself. Some imagine the LHC as a destructive giant, smashing protons together until they scream into fragments. But that image is only half true. The other half is quieter, almost meditative. Because the LHC is not a wrecking ball. It is a microscope made of energy, a lens sharpened by velocity rather than glass. When two protons meet inside its ring, they do not simply collide. They reveal, for a heartbeat, the deeper architecture of the vacuum. Richard Feynman once said, "Nature isn't classical. Damn it. If you want to make a simulation of nature, you'd better make it quantum mechanical." And that sentiment echoes through every corridor at CERN. Because the LHC works on a principle so simple it feels ancient. To see smaller, use higher energy. Shorter wavelengths, finer detail. It is a cosmic version of focusing a lantern beam, tightening the light until it can slip through even the smallest cracks in reality. Yet there is a cost to sharpening one's gaze. For energy is not a passive thing. It bends space. It curves the stage on which all particles dance. That is why the LHC is both a microscope and a threshold. A tool that approaches the limits nature herself has drawn. When it shakes the Higgs field using energies near 14 tera-electron volts, what we see is not the field directly, but its ripple, the Higgs boson. Like striking the surface of a lake to watch the wave rise from it. The LHC does not show us the water. It shows us the motion. The detectors called ATLAS and CMS are the great listening chambers of this experiment. Vast cathedrals of magnets and silicon, watching the aftermath of each collision with the patience of monks recording stars. Lisa Randall once said, "The universe is not only queerer than we suppose, it is queerer than we can suppose." And that feels true when one looks at the Bose complexity inside those detectors, where billions of events each second must be sifted to find the faint whisper of a Higgs decay. Atlas sees the broad symphony, wide, sweeping, majestic. CMS sees the finer threads, the narrow signals lost between storms of particles. Together they behave like two eyes in the skull of a single instrument, each giving perspective the other cannot. And yet, for all this power, there are limits. The LHC can resolve distances down to 1/10 of a femtometer, smaller than a proton, close to where quarks churn inside their prison of gluon fields. But the Planck scale, where quantum gravity roars to life, lies 19 orders of magnitude smaller. A gulf so vast it feels almost mythic, as if nature placed a canyon between what we can know and what we can only imagine. To reach that deep, one would need energies comparable to smashing mountains into mountains every heartbeat. A collider the size of a galaxy. Even Brian Greene once remarked that probing the Planck length requires energies far beyond anything nature has allowed us to touch. And so the LHC stands not as a final answer, but as a lantern on a long path. Here, a gentle transition arises. Because when we contemplate the limits of the LHC, our thoughts drift naturally toward the theories that attempt to describe what lies beyond. String theory, with its vibrating filaments of energy, suggests that particles are notes on an unseen instrument. Edward Witten once said, "String theory is a framework deeper than particles, a language that sings gravity and quantum mechanics into harmony." Loop quantum gravity, in contrast, imagines that space itself is woven from discrete loops of geometry, a fabric that shimmers with quantum grains. Carlo Rovelli whispered that, at the smallest scale, space is not smooth, but made of quanta, the world woven from loops of gravity. 2 visions, 2 lanterns, both reaching toward a horizon the LHC can never cross. But in a way, that limitation feels comforting. Because science is not simply about piercing the final veil. It is about traveling toward it with wonder. When I reflect on the LHC, I do not see a machine built to destroy. I see a question made of metal and magnets, a human attempt to listen to the quietest parts of the universe. Even its limits teach us humility, reminding us that knowledge is not a ladder reaching one final rooftop, but a coastline thick with fog, expanding as we walk. And the lesson I carry is simple, that curiosity itself is the instrument that brings us closer to truth, even when our machines cannot. The LHC cannot see the Planck length, but it can show to us the path that leads in that direction. It cannot part the Higgs veil, but it can make it tremble. It cannot reveal the deepest laws of creation, but it can whisper their presence. And sometimes, a whisper is enough to keep the human spirit wandering, wondering, dreaming. If you feel that wonder echoing somewhere inside you, let it rest there gently as we drift deeper into the night. In the quiet darkness between stars, where thought drifts like dust in a sunbeam, there is a question so delicate that it almost disappears when spoken aloud. Why does concentrating energy to observe the universe cause the universe to fold in on itself, creating a black hole where an answer should have been? It is a question that feels less like physics and more like listening for an echo in a vast cathedral. An echo that returns, changed, distorted, heavy with meaning. Einstein once whispered through his equations that mass and energy are 2 faces of the same coin. A truth so simple that it glows even now. E equals mech squared. A line that changed the world. When we pour energy into a small region of space, we are not merely shining a brighter light. We are gathering mass in the language of gravity. And gravity, patient and absolute, responds by bending spacetime around that gathered energy. The more tightly we focus that energy, the sharper our vision, but also the more violently spacetime curves. Eventually the curvature becomes steep enough that even light cannot escape. A silent well forms, and the experiment collapses behind its own horizon. Kip Thorne once said, "The closer you push toward a gravitational radius, the more fiercely the universe pushes back." He was right, for there is a threshold where curiosity becomes collapse, where a microscope becomes a black hole. This threshold is marked by the Schwarzschild radius, the moment when the energy we use to illuminate a point becomes its own trap. It is a strange and humbling rule, that the act of seeing creates a darkness deeper than anything we sought to observe. Yet this is not a failure of our tools, nor a cruelty built into physics, but a quiet message that the universe holds its foundations with careful hands. Physicist John Wheeler described the depths below this collapse as quantum foam, a restless froth of space-time, where geometry dances in wild uncertainty. As we push vision smaller and smaller, We drift toward that foam, toward Planck length, the final whisper before the universe falls silent. At Planck length, roughly 1.6 times 10 to the power of -35 meters, space loses its smoothness, its continuity. It breaks into something granular, pixelated, alive with fluctuations. Carlo Rovelli said, "At the Planck scale, space-time is woven from quanta. And in that weaving, everything familiar dissolves. The relationship between energy and curvature becomes a kind of cosmic poem, a balance between what we wish to see and what reality can offer. If we try to probe smaller than this scale, gravity tightens its grip, energy folds inward, and the view collapses into a gravitational shadow. This boundary is sometimes called the black hole barrier, the final refusal of nature to let itself be divided further. Some physicists believe this limit is not absolute, but an invitation to a deeper understanding. String theory whispers one answer, suggesting that particles are not points, but tiny oscillating strings. Strings grow larger as energy increases, stretching instead of shrinking, softening the singularities that threaten spacetime. Brian Greene once wrote, "The universe is a symphony of vibrating strings. And in this symphony, the smallest note cannot be played sharper, only louder." Loop quantum gravity offers a different music, one of discrete geometry and woven loops. In this vision, space-time is a fabric stitched from smallest pieces, each a quantum of area or volume. No collapse, no singularity, only the smallest stitch the universe allows. Both theories, in their own quiet way, say the same thing. There is a scale where the story of here and there no longer makes sense, where distance becomes a rumor rather than a fact. When I think about this boundary, I feel a strange tenderness, as if the universe is telling us that some things are meant to be touched only with imagination. Not because they are forbidden, but because their beauty lies in their elusiveness. We live in a world where curiosity drives us forward, upward, inward. We build machines like the Large Hadron Collider, not out of defiance, but out of wonder. Yet even the LHC, with its trillions of electron volts, cannot approach the Planck energy, an energy so intense that spacetime itself would recoil. And perhaps that recoil is natural. Perhaps it is the universe saying, "You are welcome to explore, but the foundation remains mine." The lesson I take from this, whispered between equations and horizons, is that knowledge has a rhythm, a hum, a boundary shaped not by limitation but by harmony. The Planck scale is not a wall. It is a note at the edge of perception, a reminder that reality is deeper than sight itself. Stephen Hawking once said, "The universe has not only a stranger form than we imagine, but stranger than we can imagine." And standing at the edge of the black hole barrier, I understand what he meant. Because beyond that boundary, we are not forbidden from looking, only humbled. The black hole we create by trying to see too much is not a punishment, but a teacher, reminding us that the fabric of reality has its own wisdom. It protects its most fragile patterns, hides its primordial structure, and invites us to dream the rest. The lesson is gentle, like a tide that pulls back before touching your feet. We do not need to see the Planck scale to understand its meaning, for the meaning is already within us. That there are depths beyond measurement, truths beyond geometry, and mysteries that do not diminish us but make us whole. And so, when I drift through these ideas, I feel both small and connected. Small because the universe is vast. Connected because we are made of the same physics that dreams in black holes and strings, energy, gravity, collapse, and silence. They guide us gently to the understanding that not all boundaries are barriers. Some are invitations. An invitation to wonder, to humility, to the soft truth that perhaps the universe is not a thing to be conquered, but a presence to be listened to. And in that listening, we discover not only why energy collapses into darkness, but why curiosity itself is a kind of light. A light that reaches right up to the edge of the Planck length and waits. Quietly, patiently, for us to follow. In the quiet depths of the cosmos, where distance softens into memory and time drifts like a slow breath, we arrive at a question older than physics itself. A question whispered by stars and answered only in the most delicate corners of theory. Is there a smallest size in the universe? A final grain beneath which reality itself dissolves? Physicists have tried to peel back the fabric of existence for more than a century, pushing microscopes to their limits, bending light, smashing particles together with energies so immense they mimic the universe's first heartbeat. Yet each attempt leads to the same quiet threshold, the Planck length, a scale so small that if a proton were the size of Earth, the Planck length would be smaller than a single atom resting on its surface. The beauty of this number is that it did not come from an experiment. No machine touched it. No lens resolved it. It emerged from pure reasoning, from combining three of nature's most fundamental constants: the speed of light, the gravitational constant, and Planck's constant. As if the universe itself had woven a natural boundary into its equations, a boundary beyond which measurement loses meaning. When these three constants meet, they form a single unit of length, about 1.6 times 10 negative 35 meters. Stephen Hawking once remarked, "At the Planck scale, space and time become a foam, seething with quantum uncertainty." And in that single sentence he pointed to the strange twilight realm where our understanding falters, where even the concept of before and after begins to crumble. John Wheeler called this realm quantum foam, a restless ocean where space is not smooth, but flickers like static in a forgotten radio signal. Distances stretch and collapse. Tiny wormholes appear and vanish. Energy swells and dissolves in less than a trillionth of a second. If we could shrink ourselves to the Planck scale, the universe would no longer resemble the quiet tapestry of stars above us. It would become a storm, a churning sea of possibility. The Planck length also gives rise to the Planck time, the shortest, meaningful moment the universe will allow. About 10-44 seconds. Below this, even time refuses definition. Cause and effect blur, and the familiar flow that guides every heartbeat, every sunrise, every orbit of every star, simply breaks apart. As physicist Carlo Rovelli wrote, "Time is not a river. It is a network of events." And in the Planck era, before the universe was even a trillionth of a second old, that network was tangled beyond recognition. To understand why we cannot measure anything smaller than the Planck scale, imagine shining increasingly energetic photons to pinpoint the position of a particle. Shorter wavelengths, sharper images. But at some point, the photon becomes so energetic that it bends space around it, creating a tiny gravitational well. Increase the energy further, and that well deepens into a miniature black hole. In trying to look closer, you erase the very information you seek. This elegant trap is known as the black hole limit of measurement, a physical law that tells us the universe protects its smallest secrets with gravity's own hand. As Kip Thorne once said, the closer you get to a black hole's event horizon, the more violently the laws of physics resist your intrusion. At the Planck length, every attempt to observe, every measurement, every photon, triggers that resistance. This is why there is no such thing as half a Planck length, because below that threshold, the very notion of distance dissolves. The universe does not hide a smaller world beneath it. It simply does not permit one to exist in any way that we can describe. And so physics finds itself standing at a cosmic shoreline, watching waves of uncertainty crash at its feet. Beyond that shoreline lies the Planck era, the earliest moment in the Big Bang, when the universe was smaller than an atom, yet packed with all the energy that would become galaxies, stars, oceans, and life. We cannot peer directly into that moment, but its imprint lingers in the cosmic microwave background, the oldest light we can see. Some theories imagine what lies beneath this threshold. String theory proposes tiny vibrating filaments, loops of energy that can never shrink smaller than their natural length. Loop quantum gravity envisions a lattice, a woven fabric of quantized space, where area and volume come in discrete units. Others suggest spacetime emerges from quantum entanglement, like a tapestry woven from relationships rather than threads. In my own view, the existence of a smaller scale is not a limitation. It is an invitation to humility, a reminder that the universe has boundaries not because it is small, but because our language breaks around truths too subtle for straight lines and simple coordinates. The Planck scale teaches us that reality is not a rigid structure, but a whisper, a rhythm, a pattern of relationships that only becomes clear when viewed from afar. The lesson is simple, yet profound. Not all mysteries are meant to be dissected. Some are meant to be approached with reverence, letting their presence reshape the way we think rather than the other way around. In this sense, the smallest scale is not an obstacle, but a teacher, reminding us that knowledge is not only about seeing, but about understanding our limits. And perhaps, as we drift through the quiet dark between galaxies, listening to the universe breathe. We realize that the Planck length is not the end of our journey, but the beginning of a deeper form of wonder. For what could be more beautiful than a cosmos so vast? It contains worlds we can never touch, and so delicate that its smallest scales vanish into silence. And maybe, in that silence, the universe is inviting us to listen more closely than ever before. In the quiet depth of modern physics, there is a question that lingers like a lantern suspended in the dark. Does Heisenberg's uncertainty principle change when gravity enters the stage? It is a gentle question at first glance, almost delicate. Yet beneath it lies a clash between the two greatest languages of the universe, quantum mechanics and general relativity. And the space where they meet is as fragile as frost forming on a silent windowpane. When we try to measure the position of a particle with extreme precision, we always pay a price. Heisenberg taught us that the tighter we hold on to position, the wilder momentum becomes. It is as if nature hides its smallest coordinates behind a veil, allowing us only a soft outline, never a sharp edge. But this familiar uncertainty changes its rhythm when gravity begins to hum beneath the equations. Because every photon we use to probe position, every burst of energy, bends spacetime just a little. At low energy, this curvature is nothing more than a whisper. At high energy, it becomes a weight that presses into the geometry itself. One of the most elegant images ever spoken about this came from John Wheeler. Spacetime tells matter how to move, and matter tells spacetime how to curve. But he did not add the quieter truth hiding between his words. Measurement itself becomes a kind of matter, a disturbance, a presence. And when it becomes too intense, it curves space-time like a fingertip pressing into soft sand. Imagine shining a photon onto an electron, trying to pin its position precisely. The shorter the wavelength, the sharper the resolution. Yet the shorter the wavelength, the higher the photon's energy. And the higher the energy, the greater its gravitational influence. Eventually, that photon begins to alter the very region it tries to illuminate. Like lighting a candle, only to watch the flame warp the air around it. This is where the traditional uncertainty principle blossoms into something deeper. The generalized uncertainty principle. It whispers that as energy grows, as curvature deepens, measurements sharpen only up to a point, then blur again. Precision becomes a circle rather than a line. The harder you push, the further clarity slips away. And here, we find a remarkable connection to the physics of black holes. Stephen Hawking once said, "Black holes aren't the eternal prisons we once imagined." But their true lesson is even more subtle. Any attempt to force too much energy into a confined region creates an event horizon. Instead of revealing truth, the measurement collapses into darkness. Instead of resolving structure, the attempt generates a boundary that hides it. This boundary, born from energy density, gravity, and the attempt to measure, echoes the famous deep inelastic scattering experiments that first uncovered quarks. Those collisions showed that the smaller the world we wish to see, the more violent the probe must become. And yet, when that violence grows too intense, it begins to change the very thing it touches. At the quantum scale, this violence becomes curvature. At the Planck scale, it becomes collapse. This is why some physicists say the universe gently protects its smallest secrets. Leonard Susskind phrased it simply: "The world is not made of things, but of information. And information cannot be squeezed indefinitely into a point." The holographic principle rises from this logic, showing that the information in any volume of space, even a black hole, is encoded on its surface, not its interior. Meaning grows outward, not inward. Distance ceases to behave the way intuition demands. The deeper implication is tender and astonishing. Uncertainty is not merely a property of particles. It is a property of space, of gravity, of the relationship between energy and curvature. It suggests that beneath the world of electrons and quarks, even beneath spacetime itself, lies something relational, something woven. Perhaps, as Carlo Rovelli says, the world is not made of objects, but of events. And so the uncertainty principle, once a rule about momentum and position, becomes a lantern illuminating a larger truth, that knowledge itself has limits. And those limits come not from our weakness, but from the universe's architecture, a kind of cosmic compassion, preventing our measurements from tearing the fabric of reality. From a personal perspective, I find a strange comfort in this, that there are domains we can approach, but never touch. That mystery is not a flaw, but a feature. It reminds me that the cosmos is not a machine with every gear exposed, but a living tapestry whose smallest threads shimmer beyond grasp. And perhaps that is why humans continue to ask, and wonder, and dream, even knowing that some answers lie forever beyond the horizon of precision. The lesson I take from this is simple, yet quietly profound. The universe is not hiding from us. It is teaching us to look with humility, to measure gently, to remember that certainty is not always the true path to understanding. Sometimes, the blur itself carries meaning. And so, as we drift forward into the next ideas waiting in the dark, let this question stay with you like a soft echo under the stars. If gravity deepens uncertainty, then what waits at the very edge of precision? What happens when space-time itself becomes the thing we cannot measure? In the quietest corners of modern physics, there is a question that lingers like a soft echo in a vast cathedral of ideas. Are the particles that make up our world truly points, infinitesimal and sharp, or are they something more fluid, more musical? When string theory first appeared, it arrived not as a proclamation, but as a whisper, a suggestion that perhaps reality is woven from tiny vibrating strands rather than perfect geometric dots. And in that simple shift, a deeper mystery was revealed. The mystery of why our equations had been collapsing into infinities for decades. In the old picture of point particles, all energy could concentrate into a single location. When two particles collided, The mathematics forced energy toward an infinitely small point, leading to impossible numbers, gravitational spikes that stretched toward infinity. Richard Feynman once remarked that these infinities were like the monsters in the basement of physics, always waiting to swallow any attempt at deeper understanding. And for a long time, no one knew how to tame them. But string theory offered a different vision. Instead of points, it pictured each particle as a vibrating loop of energy, a one-dimensional filament whose length spread the energy across space. In this form, no collision could focus energy into a perfect point, and therefore, the infinities that haunted earlier theories simply dissolved. As Edward Witten beautifully observed, string theory is the first framework where gravity and quantum mechanics dance together rather than collide. This softening of energy has profound consequences. When you try to push a string into a smaller and smaller space, the string does not shrink like a point particle. Instead, it fights back. It vibrates more wildly, absorbing the energy as new harmonics, stretching itself rather than collapsing. At extremely high energies, strings actually grow in effective size. This means the universe simply refuses to let you zoom in forever, protecting itself from the infinities that once threatened to tear its mathematics apart. Even gravity emerges from this gentle behavior. Among the countless vibrational modes of a string, one particular resonance behaves exactly like a massless spin 2 particle. The graviton. Gravity is not an added ingredient. It is a natural song the string plays when it vibrates. And in this way, string theory marries the quantum world with Einstein's curvature of spacetime, letting both exist in the same elegant frame. Brian Greene once said, "The universe is a symphony, and string theory reveals the notes." To allow these strings to vibrate consistently, the universe must possess more dimensions than the 4 we know. The extra dimensions fold into intricate shapes called Calabi-Yau manifolds, little curled spaces that hide within every point of ordinary reality. Their geometry determines the tones strings can play, just as the body of a violin shapes its sound. If the universe had chosen a different Calabi-Yau shape, the particles and forces we know might never have existed. There is something deeply poetic in the thought that the structure of atoms, the birth of stars, even the chemistry of life, may depend on the curvature of hidden dimensions curling silently beneath our feet. As we step back and see how these ideas connect, a natural bridge appears to the work of the LHC. The great ring where protons are guided to near light speed to stir the Higgs field. The Higgs boson itself, discovered through delicate signatures in the ATLAS and CMS detectors, is a reminder that fields, not particles, are the true foundation of nature. And in that spirit, strings can be seen as deeper ripples in a deeper sea. The sea from which the Higgs field, gravity, and quantum forces all arise. Lisa Randall once reflected, "The structure of the universe may be much richer than the 4-dimensional world we perceive." I find myself returning to that thought often, especially when considering why string theory avoids the catastrophic infinities that plague point-particle physics. The answer, to me, feels almost philosophical. Points are rigid, brittle, unforgiving. Strings are supple, resonant, capable of transforming chaos into harmony. A point collapses under pressure, but a string sings. And perhaps this is why the mathematics grows calm and finite when particles are treated as strings rather than dots. There is a gentle lesson in this. Nature, at its smallest scales, may not be built from things, but from relationships, from vibrations, from patterns that weave themselves through time and space. When we imagine matter as points, we imagine isolation. But when we imagine matter as strings, we imagine connection. Perhaps that is why the infinities fade away, because strings refuse to exist in perfect loneliness. As the energy of a probe increases, a point-particle model forces all attention into a single, infinitely sharp spot. But a string spreads the energy, distributes it, dissolves the singularity before it forms. In this way, string theory keeps the universe smooth where older theories made it tear. It evokes gently a universe that protects itself from our attempts to peer too closely. A universe that answers harsh questions with soft boundaries. Still, this elegance does not mean completeness. Much remains untested, and some critics point out how vast the landscape of possible Calabi-Yau shapes is, how difficult it is to extract a single empirical prediction. Yet even among these uncertainties, the idea continues to captivate, perhaps because it invites a way of seeing the world that feels fuller, more coherent, more unified. As Stephen Hawking once said, string theory has the remarkable property of including gravity automatically. That alone hints we may be touching something essential. When I reflect on this, I am reminded that theories are not only technical structures, but mirrors. They reflect how we imagine the world, how we imagine ourselves within it. A point-like particle reflects a universe of isolation, a universe of tiny islands. But a string, vibrating and resonant, reflects a universe made of relationships, of waves passing through one another, of harmony woven into geometry. Perhaps the deepest lesson is that the universe does not fear being examined. It simply invites us to use a gentler touch. To see its smallest truths, we must abandon the idea that reality is a collection of hard points, and instead accept that it may be a tapestry of vibrations. A cosmic instrument whose strings play gravity, matter, and light. When we approach it with rigidity, the equations explode. When we approach it with softness, the infinities fall silent. And so, string theory's ability to avoid infinities is more than a mathematical trick. It is a philosophical turning point, a reminder that the universe may prefer resonance over collision, music over geometry, flow over fracture. The more I learn about this theory, the more I feel that understanding does not always come from pushing harder, but from listening more closely, letting the equations breathe, letting the universe hum its own quiet melody. Maybe that is the real gift of string theory. Not certainty, but a way of seeing, a way of imagining a cosmos that avoids infinities because it is made not of points, but of songs. And somewhere within that music, perhaps, we will one day hear the soft resonance that explains not only strings, but the Higgs field explored at the LHC, the curvature of spacetime, and the delicate architecture of reality itself. Until then, we follow the vibration, gentle, persistent, a thread of meaning stretching through the dark, guiding us toward a universe that whispers rather than shouts, a universe that teaches not by breaking, but by resonating. At the quiet edge of modern physics, where equations soften into wonder, a simple question begins to echo through the halls of science. Is space-time truly smooth? Or is it woven from tiny grains that no human eye can ever see? Some call these grains the atoms of geometry, quanta of area and volume, subtle pulses of existence that stitch the universe together. And as we drift deeper into this mystery, the world as we know it begins to tremble in the soft light of possibility. Physicist Carlo Rovelli once whispered, "Space is not what it seems. It is granular, woven from loops of gravity." His words hover like dust motes in starlight, suspended, patient, waiting for us to listen. For if he is right, the universe is not a grand continuous stage, but a lattice of quantum nodes, each one the smallest heartbeat of reality. Loop quantum gravity proposes this gently, not with the thunder of certainty, but with the humility of a theory that knows its place at the frontier. In this view, space is built from spin networks, shimmering meshes of relation rather than position. A node becomes a quantum of volume, a link becomes a quantum of area, and when countless of these units overlap, the illusion of smoothness blooms. Just as a distant mountain ridge looks like a single curve, even though it is carved from a million stones. And time, that silent river we float upon, is no longer a continuous flow, but a sequence of quantum ticks, each one a spark of becoming. At the smallest scales, the universe does not move smoothly forward. It shimmers, pauses, leaps. Time may be an illusion, albeit a stubborn one, Einstein once mused, and his voice lingers here like a lantern in a darkened cave. If space is grainy and time is discrete, then the beginning of everything must be reconsidered. Perhaps the universe was not born from a singular explosion, not from a point of infinite density and no size. Perhaps it emerged from a bounce, a turning of the cosmic tide, where a prior universe contracted, reached a minimum, then expanded again. A rhythm rather than a birth, a pulse rather than a beginning. The Big Bounce is not only a scientific proposal, it is a philosophical comfort. It suggests that nothing comes from nothing, that even before our universe awakened, there was motion, structure, possibility. In this view, every galaxy we see today is an echo of cycles, far older than our imagination permits. Yet these ideas must confront a deeper question, one raised by the generalized uncertainty principle, the GUP. If every act of measurement disturbs space-time, bending it under the weight of its own energy. Then precision becomes a kind of illusion. As we try to measure smaller distances, we use higher energy, and that higher energy curves space, twisting the very coordinates we hoped to reveal. At the limit, the universe protects its secrets, forming a tiny gravitational well that hides what lies beyond. Stephen Hawking once said, "The closer you get to the horizon, the stranger time becomes." And at the Planck scale, even strangeness itself seems to dissolve. The GUP whispers a quiet truth, that the universe does not allow infinite sharpness, that there is a smallest meaningful length where all our tools fail. Below it, distance is not merely unknown, it is undefined. This ties back to the granular vision of spacetime, where the smallest areas and volumes are like the pixels of a cosmic screen. But these pixels are not placed onto space, they are space. Their relationships form geometry, their interactions form gravity, and their collective harmony becomes the world we inhabit. When I reflect on these ideas, I find a quiet lesson tucked between the equations. That the closer we look at reality, the less it behaves like a rigid structure, and the more it resembles a poem of relationships, not objects, of processes, not positions. If spacetime is woven from connections, from the delicate interplay of quantum states, then perhaps we too are part of that woven tapestry. Our lives, our choices, our meanings, all threads in the same subtle cloth. It teaches me humility, knowing that the ground beneath my feet is not solid, but a sea of flickering quantum geometry. It teaches me wonder, knowing that every moment unfolds upon a lattice of space-time that vibrates with ancient memory. And it teaches me patience, because some truths are not meant for our eyes, only for our imagination. As our instruments improve, as NASA, ESA, and the world's observatories listen for subtle whispers from the early universe, we may one day see hints of this granular world, a flicker in the polarization of distant light, a delay in a gamma-ray burst, a tremor in a gravitational wave, each a message from the smallest scales, carved into the fabric of the cosmos long before Earth even existed. Until then, we drift in gentle speculation, guided by the voices of those who came before. As John Wheeler said, space-time tells matter how to move, and matter tells space-time how to curve. But even he suspected that beneath that dance, something deeper waited to be understood. And so we float here, between knowledge and mystery, between the smooth illusion and the granular truth, listening, wondering, dreaming, because perhaps the universe is not made of space, but of stories. And every story, even the cosmic ones, is written one quantum at a time. If you feel a quiet stirring within you now, a sense of awe or a gentle question, leave a comment, like a lantern placed along a dark cosmic path. A reminder that even here, at the smallest scales of existence, we are wandering together. At the quietest edge of modern physics, there rises a question so simple and yet so disarming that it softens even the most confident theories. Does distance truly exist? Or is it only a convenient story we tell ourselves? A kind of cosmic lullaby whispered to help us navigate a universe far stranger than our senses admit. When I think about this, I find myself drifting the way starlight drifts through deep space. Slow, unhurried, weightless. Because at the Planck scale, that unimaginably tiny realm where quantum uncertainty shivers alongside the pull of gravity, the very fabric of measurement seems to dissolve. And once it dissolves, everything we thought we knew about here and there, near and far, before and after, begins to slip from our fingers like dust illuminated in a shaft of cosmic light. Einstein taught us that distance is not fixed, that it stretches and bends with mass and motion. Quantum mechanics tells us that precision has limits, that the closer we look, the more reality trembles beneath our gaze. Yet when these two visions meet, when quantum rules collide with gravitational curvature, something even more extraordinary happens. As physicist John Wheeler once said, at the smallest scales, space is a froth, a tumult of uncertainty. And that froth, that quantum foam, may be the first hint that distance is not truly fundamental. As we descend deeper, following the path carved by the smallest particles, the metric of spacetime begins to deform. And then, almost reluctantly, it collapses. Not in a violent way, but like a quiet surrender, like watching frost melt from a window at dawn. At the Planck length, roughly 10 to the minus 35 meters, the concept of where something is becomes meaningless. Nima Arkani Hamed captured this beautifully when he said, "Space-time is doomed." He didn't mean destroyed, but revealed, unmasked, shown to be only an approximation emerging from something more primitive. In this view, distance is not a built-in feature of nature, but a mirage formed from deeper relationships. Space is not a stage, but a story. And the true actors behind that story may be quanta of information, woven together through entanglement. This brings us to a remarkable idea that has reshaped the way many physicists think about reality. Space, the very arena of existence, may emerge from the connections between quantum states. Connections not measured in meters, but in correlations, in shared information. Leonard Susskind once said, "Space is stitched together by entanglement." And the more I sit with that sentence, the more it feels like poetry whispered by the universe itself. Imagine that what we call distance is nothing more than the strength of a relationship. That two particles appear close when they share information, and far when they do not. Like two strangers who feel worlds apart despite sitting side by side. Or two lovers separated by continents, yet bound by a thread no map can show. That is the kind of intimacy quantum physics offers. An intimacy so subtle that it births the illusion of space. And if space emerges from entanglement, then space-time itself is a tapestry woven from quantum threads. Each thread a whisper, each knot a moment. This idea reshapes the question of what distance means. For if distance is an effect, not a foundation, then the smallest scale in the universe is not merely small, but transformative. Some of the world's leading thinkers have echoed this sentiment. Carlo Rovelli once wrote, "Space is not an empty box. It is a dynamic field of relations." Stephen Hawking reminded us, at the deepest levels, space-time becomes uncertain. And Richard Feynman said, "Nature is imagination in a straitjacket." A reminder that what we perceive is shaped by the tools we carry. As NASA's JWST peers deeper into cosmic history, as LISA prepares to listen to gravitational murmurs across billions of light-years, and as future missions measure the trembling of space-time itself, we may find signatures of this emergent universe. Perhaps tiny delays in the arrival of photons, distortions in gravitational waves, or subtle noise patterns in the cosmic background will reveal that space-time is not smooth, but grainy, not fixed, but fluid. Sometimes, I think that what moves us is not the equations, not the experiments, but the humility they teach. When the smallest scale in the universe tells us that distance itself may be an illusion, we learn something profound, not just about physics, but about ourselves. We learn that certainty is fragile, that understanding is layered, and that even the most familiar truths may be shadows cast by something deeper. And there is a lesson tucked gently inside this realization. If space can emerge from entanglement, then perhaps our own connections, the way we share thoughts and emotions, are part of the same universal pattern. That meaning is born not from isolation, but from relationship. That closeness is not measured in miles, but in resonance. As I reflect on this, I find myself feeling both smaller and larger at the same time. Smaller, because the universe is stranger than I ever imagined. Larger, because somehow, even in that strangeness, we still belong to it. The laws that dissolve distance at the Planck scale, the entanglements that stitch together space-time, the trembling foam beneath creation, all of it includes us. A universe where distance is not real, where space-time emerges, where geometry is woven from information, is a universe that invites awe. It invites a calmer kind of curiosity, one that does not demand answers, but embraces the beauty of not knowing. And perhaps that is the quiet gift hidden in the smallest scale in the universe. Not certainty, but wonder. Not clarity, but humility. Not a final answer, but a gentle reminder that reality has more layers than our minds can hold. So as we drift through this cosmic meditation, through ideas that stretch and soften the meaning of distance itself, I leave you with a question that continues to echo in my thoughts. If space is not fundamental, if distance dissolves at the Planck scale, then what is the universe really made of? And what does it mean that we are part of it?